Okay, so today we're continuing our series on the planet Mars by watching Mars Chemistry Looks for Life. That's what we're watching today. Mars Chemistry Looks for Life. And this is by Chem Study, College of Chemistry, UC Berkeley. Okay, interesting. We've watched a bunch of UC Berkeley stuff before. I think a lot of the Galapagos programs were also UC Berkeley, so this should fit in nicely with the stuff we've watched in the past. But this was published all the way back in 1978, so a little bit after, the initial space race. This is probably when we actually had some information about Mars, right? The title is Mars Chemistry Looks for Life. I think we're in like the second stage of studying Mars, where we sort of know what it's like, but we don't actually have an understanding of it quite yet. So this should be a really interesting early look at our understanding of life on Mars. So let's dive in, shall we? Oh man, instantly we are confronted with this old image of Mars, though, with these weird straight lines on it that people mistook for canals. Like, this is already an outdated image. I think the people who made that understand that. I think this is a purposeful inclusion of an old image. Yeah, Regents of the University of California. Interesting. So this is more of like a college-aged program, I think. This is more advanced than what you'd be showing to high schoolers. All right, collaborator. So here's the professor in charge was George C. Pimentel from the UC Berkeley, and producer was David Ridgway from the Chemical Education Material Study. That must be what chem is. So I wonder if these are like the personal writings or the thoughts of George C. Pimentel. Like, obviously the information in this is going to come from a lot of, respected sources, but I have to imagine George C. Pimentel was the one to collect all these ideas to some degree.
Beyond our own planet.
Whoa, that was a good edit, and this is also an impressive visual. Like, we're flying through a field of stars right now. I don't know how exactly they made this effect. They probably got a whole bunch of layers of glass and just, parallaxed them a certain way, but like, I don't know, this is a cool shot for sure.
Does life exist anywhere else in the universe?
That's so interesting that's the first question that's posited, because that's literally the first question I posit in my own video about Mars, right? Like, that is why we're here to begin with. That's why we're so interested in Mars. No one's interested in Mercury, no one's interested in Venus or Jupiter or whatever to the same degree that they're interested in Mars, because Mars is the one place where that question actually has a slightly interesting answer. So it's cool to see that even back then.
Could life exist on one of the other planets in our own solar system? To seek an answer to this question, scientists sent the Mariner spacecraft flying past Mars in 1967, 69, and 71.
The Mariner program in 67, 69, and 71. That's interesting. So that overlaps with the Apollo program. See, this is like the hard part of understanding space exploration. It's just that like we were doing all of it sort of simultaneously. It's hard to keep track of it all. But all right, so the Mariner programs to Mars, 67, 69, 71. That's when we were learning about Mars for like the first time ever, pretty much. So yeah, this coming from 78 means that we actually do have some degree of understanding of the planet already. Also, very impressive animations so far, just in general. And the music. The music is like very, very dramatic.
The Mariners photographed sections of Mars and made scientific measurements as they flew past the planet.
Oh yeah, I feel like the last Mars program we watched was kind of them piecing these globes together like this, right? Again, it's probably been like a month since I last recorded for this channel, and probably more since I last recorded a Mars program for this channel. So I'm kind of forgetting what I watched last, but I'm pretty sure this is like lining up pretty nicely with the last Mars program we saw.
The images and the data were transmitted back to Earth.
thing. I love seeing like how the computers like worked back then. Like seeing the operating system, like Mariner 6, picture 076, July 31st, 1969. Like even this little like graph that just formed. Like it's so interesting seeing how the technology was back then. Like it's hard to describe, but like I have no concept of what computers from 1969 looked like, but except through programs like this. So it's so fascinating that this is the most advanced computer that we are using to study like the most advanced scientific operation we had ever really pulled off by this time. Sending probes to other planets and having them send us pictures back. You know, like this was so advanced for the time. It's incredibly impressive, the machines that we're looking at right now. Even though from our perspective this all looks old and, you know, junky, it's like, no, like when this was taking place, this was like future. This was actual like future sorcery magic, and it still sort of is.
A thin carbon dioxide atmosphere was confirmed.
Dang, yeah, look at these close-ups. I've definitely seen this image before, but yeah, you can see the haze of the atmosphere in the valleys as opposed to the plateaus. Like, it's so cool to study Mars from like a geophysics standpoint because there is so much similar to the Earth that you can just observe from the surface.
Also the presence of moisture. Daytime temperatures, much like those on Earth, were measured. But every night,
daytime temperatures much like those on Earth. So I don't know if they're just saying that like it warms up during the day and cools off at night, because yeah, that makes obvious sense. But I would not make the claim that Mars experiences similar daytime temperatures to Earth. Like maybe the warmest days on Mars are about as cold as like, honestly, it reaches about 60 or 50 degrees on Mars sometimes, but the atmosphere is a lot thinner, so it's different. I would not describe Mars's temperature as anywhere near Earth's temperatures.
But every night, the temperatures drop to minus 50 or 60 degrees centigrade.
Yeah, minus 50 or 60 then.
Even near the equator. Could simple life forms exist in such an environment?
That's so, I have literally said that statement almost verbatim in my videos before. So it's so almost cathartic to be hearing it asked in the same exact tone from all these years ago as well. It's just, it reminds me that like I am not the first person asking these questions or even making, you know, educational programs surrounding these questions.
Could they have existed there in the past? The only way to...
Like, that's literally the conclusion of the video I'm working on, is those questions. That's like, I love hearing that.
To learn more was to land instruments on the surface of Mars. Instruments whose measurements would give more evidence about the presence or absence of life on the red planet. The Viking spacecraft were designed to do that.
Dude, the music picking up, like I'm getting into it now. And the animations, dude, oh, this is so fun. Oh, this is an animation. This looks like a miniature, actually, doesn't it not? Yeah, there's no way this is animated. The reflection on the gold foil, this has to be like a real model.
66 feet, 73 feet per second. ACS is close to vertical.
So we're coming down, straight down.
Nav is green for touchdown. ACS is green, 1 point.
Is this really the Mariner probe? Is this how the Mariner spacecraft landed on Mars?
5 degrees per second max, 0.2 Gs.
Dude, look at all these rooms, too. Look at all these old telephones and computer monitors. Again, wild that we landed stuff on Mars using all this equipment. I guess it shows that it's not that hard. Like, we were able to do it when our computer technology was, like, very primitive still. So the fact that we haven't been to Mars in a significant way since then, well, I guess we've sent rovers. But, like, getting to Mars isn't that impressive when you realize, like, this is all it took, really, is these sorts of computers.
The numbers have no fundamental
the predicted landing time.
give you, but as soon as they change drastically, we'll have to...
There it is. Yeah, good 16 kilometer data.
Wow, hang on. Is this like the first photo taken from the Mariner lander? Or the Viking? No, it's the Mariner, right? Yeah, I think it's the Mariner. Yeah, this must be like the first photo it sent back. That's incredible. Wow.
On July 20th,
Yeah, there you go. First picture from Mars' surface.
1976, the first Viking lander touched down on the surface of Mars.
Hang on, 76, the first Viking. Oh, so it was the Viking lander. The Mariners passed by Mars, but the Vikings actually landed on Mars. Got it. Okay, that makes sense. I'm glad I actually got myself confused earlier about that. But all right, this is from Viking. This is 76. We're landing on Mars for the first time. See, again, like, was that an event for people back then? Were people like losing their minds because we landed on Mars, or were people even paying attention to this sort of stuff? Like, I have to imagine some people were losing their crap, but like some people, but I also have to imagine very few people actually cared.
Like we've got 16 kilobit data. Great, thank you.
When the Viking mission was being planned, scientists had to decide what experiments would be best to send to Mars when it's not known what kind of life might be there.
That's so funny that it's not known what kind of life might be there. Like, before we really went to Mars, we were a lot more optimistic about finding life there. Like, we just thought it was almost a certainty that there would be life there. So it's funny. It's just funny to hear our old perceptions of Mars and how the things that we've discovered have influenced our thoughts since then. Because I definitely feel like I know more about Mars than any of these people, just by virtue of the fact that I exist during this time period.
On Earth, life is found almost everywhere.
I love how this is the frame used for life. What is this, like a walrus like sucking on a glacier? Yeah. Yeah, I really hope there's this sort of life in Mars as well. Oh, okay, we're getting a montage. It's not just the walrus, but I thought the walrus was a funny first illustrator of life. And the music is so upbeat too. I'm jamming out to this soundtrack right now.
And in seemingly infinite variety.
A very strange, very eclectic edit of animals and humans together. Like very, I don't know where they sourced all these clips, but it seems almost random where they got some of these from. Like, this must just be like the UC Berkeley like film archive that they just used these from, right? Like, there's no way they filmed all of these just for this program. Like, this must be used from some sort of library.
Despite the variability of life on Earth, there are some properties all life has in common.
That's so funny too. Again, like, I say almost the same exact thing in my video. Like, not the same exact thing, but I say that if there was life on Mars, it most likely would have followed the same patterns of evolution as life on Earth. And that's what they're saying here as well. That, like, even though there's such variety, like, life always does pretty much the same thing. Weird how they're showing two humans kissing to illustrate that, but yes, life wants to reproduce. I can only imagine Martian life will also kiss each other on the mouth to reproduce. I would love to see that, two Martians mouth kissing.
One such property is reproduction.
Yeah, reproduction, that's the point, that's what I'm talking about.
Survival of each species depends on its ability to reproduce. During its lifetime, a parent can have many children.
You know, it just struck me that, like, these people don't really realize that there are, like, no macro animals on Mars whatsoever. Like, even in the most ideal of conditions ever, there would never have been animals or anything like an animal, not even something multicellular on Mars. That's the whole point of my video, is I track the timeline of when Mars was habitable compared to the pace at which life evolved here on Earth. And what we'll find is that there never could have been anything more advanced than photosynthetic life. And even photosynthetic life is a very iffy suggestion to make in the context of life on Mars. Like, I would be willing to bet the only life that actually truly existed and thrived on Mars was chemosynthetic. So it's so funny to see them positing there being sea turtles on Mars. Obviously, they're not really suggesting it, but by including it visually, they sort of are at the same time.
In this way, the population of a species can increase. Under favorable conditions, the population growth of any life form occurs with a characteristic time behavior. This characteristic time behavior of reproduction provided the basis for one of the Viking life search experiments. The time behavior or rate behavior that characterizes reproduction can be seen by watching these human cells divide.
Wow, these are human cells. That makes this a little bit more interesting.
Under favorable conditions, one cell becomes two. Two become four.
So yeah, they're saying that like even at its most basic, life always multiplies itself in, observable, quantifiable ways. So it must be a way we can observe and quantify life doing the same on Mars, which is kind of sad that we haven't, because this is like a pretty obvious way to find life. So the fact that we haven't found life through this means it's probably not there, or at least it's not exactly where we're looking. I have my own theories as to where life is on Mars. I guarantee you, if you took a drill and drilled like 50 feet or 100 feet down into the crust, you'd find some form of a single cellular life. But on the surface, I doubt there's anything like this.
In turn, each new cell may also divide. The important characteristic of this reproduction process can be seen on a graph. 4 cells become 8. 8 becomes 16.
Okay, so yeah, it's just going to be like an exponential growth formula, right?
And so on. The number of cells plotted against time follows a curve that becomes steeper and steeper. This
Hang on, this curve doesn't really match the the steepness of the actual graph, but whatever. It gets the idea across, I guess.
increasing rate of growth is a characteristic of every life form placed in a favorable environment. This time behavior...
See, that's funny. That's funny how they said this is characteristic of every life form placed in an ideal environment, because there's two sort of population graphs that go like this. There's the J curve and the S curve. If you know your population science, J curve is very similar to like this. It just keeps going up and then crashes down once the carrying capacity has been overwhelmed and the resources of the environment can no longer support the population. Or there's the S curve where you go up and then you level off and go up and down regularly. So I don't know. I guess my understanding of population dynamics might be a little bit different than the ones they were using for looking for life on Mars.
where the rate of growth of a population increases in proportion to the population is called exponential growth. Exponential growth is a property common to all life forms.
Yeah, I guess that's true. Both J curves and S curves both start out with exponential growth. So yeah, you will definitely be able to observe exponential growth in life multiplying. Again, I don't know how exactly you quantify that in terms of searching for life on Mars. Like, I don't know what sort of experiment you do to look for exponential growth, but I'm curious now.
Another property common to life is the consumption of nutrients and the production of waste products. For example, every living cell consumes nutrients and gives off end products such as carbon dioxide.
I like how simple this graph is. Nutrient metabolic cycle. Like nowadays we'd call this like, oh man, what would we call this? Not the Krebs cycle. This is like, I guess this is just metabolism, right? This is just like cellular respiration. Yeah, that's pretty much what it is. It's pretty much just cellular respiration that we're looking at.
The formation of the end products occurs at the same rate as reproduction. Scientists would say both occurrences exhibit the same time behavior characteristics, or reaction kinetics. If an end product, such as CO2, is detected, the time behavior or rate of its formation can reveal whether a reproduction process could be responsible.
Yeah, that's very fair. Very basic, but very, understandable and fair at the same time. Like, if there is an exponential increase in the production of CO2, we can assume that there's an exponential increase in the things that are producing the CO2, which probably means some living organism is reproducing at exponential rates because that's what living things do, and producing CO2 at the same time. I wish we had some sort of discovery like that relating to Mars, but we don't. Unfortunately, I don't think we've ever observed CO2 coming out of the Martian soil after adding water. Maybe, though, I don't know. I'd be very interested. I have to imagine we've done that experiment, but I also have to imagine if we've received certain results, I'd already have known about that.
Here is a simple apparatus with which we can measure the time behavior, the reaction kinetics of chemical
I
reactions.
guess we've never brought material back from Mars, though, have we? Like, that's what the InSight was all about, right? Those packing up the Martian material in those tubes. So maybe we never have done this experiment. I don't know.
Let's begin with the inorganic reaction of sodium carbonate with hydrochloric acid. This flask contains sodium carbonate. Dilute hydrochloric acid is introduced into the collecting funnel.
I don't quite get how this relates to looking for life on Mars, but this should be good. I guess it's called Chemistry Looks for Life, so I should have expected to see some beakers like this. This will actually be a learning lesson for me, I think.
The reaction generates carbon dioxide, which moves through a glass tube to displace a column of water in a graduated cylinder.
Okay, that's simple enough. So now are we going to replace the sodium whatever with Mars material and see if it produces gases too? That's where my head is.
In the first 30 seconds, 150 milliliters of CO2 is collected.
I like how scientists used to just write things on like graph paper, I feel like nowadays you would print out like a table with all this information on it and it would all be printed and maybe you would hand write the results, but like here it's just like, no, I constructed this table by myself, like Na2CO3 HC2 experiment, like sodium carbide hydrochloric acid experiment, like this. It's all handwritten. I think that's hilarious.
After another 30 seconds, only 15 milliliters of additional CO2 is produced, giving a total of 165 milliliters. The reaction is slowing down. In the next 30 seconds, only 5 milliliters of CO2 is added. We see that for this reaction, in each succeeding 30-second time interval, less end product is formed than in the preceding time interval.
Oh, okay, so I get it. So there's clearly nothing alive in this experiment because the volume of CO2 is not increasing exponentially, it's decreasing seemingly exponentially, or really just sort of linearly. Probably not linearly, but it's definitely a curve, and then it levels out as well. And the reason it's decreasing is because nothing in that original beaker is producing any more of CO2 or anything, whereas life, is constantly producing more waste products, so you would have more produced over time.
This kind of time behavior, reaction kinetics, occurs when a reactant is being used up. Let's contrast this time behavior with a growth process. Ordinary garden soil can demonstrate the reaction kinetics of living, reproducing organisms. Such soil contains numerous microorganisms.
What's he growing in his garden? I want to see. I'm so curious. What are they growing in this lab, huh? Like, why do they just have a garden on this premises? What experiments are being done with this garden? I'm so curious.
The experiment is started by placing about 20 grams of the collected soil into the same apparatus we used in the experiment with sodium carbonate. For this reaction...
All right, so my guess is you're going to get a lot less CO2 initially, but it's going to continually produce more instead of diminishing over time.
For this reaction, we will use a nutrient solution that will encourage growth of the microorganisms.
What's the nutrient solution? Oh, I'm so curious. What is it? Is it just like compost tea or is it like something specific? I don't know. That's what I want. I always want them to explain everything to me. I understand why they don't, or else this would take forever, but at the same time, I'm just too curious not to ask. Here's the thing. If I ask, some of you might have an answer for me in the comments. That's why I bother to ask, is because somebody will know what this chemical is just based on its weird color and the context of the experiment.
The nutrient solution contains sugars, amino acids, vitamins, and seawater.
Oh, okay, so he just explained it to us. That's actually very interesting. There's sugar, amino acids, vitamins, and seawater. That's very interesting. I wonder why seawater. Like, isn't the salt going to affect something? I don't know. That's just, I mean, maybe the seawater is just to have like as many different microorganisms as possible in it. Maybe that would help somehow. I don't know, but like, that's an interesting concoction. I guess that's probably trying to imitate like early earth water maybe or something. I don't know. That's interesting.
Things microorganisms like to eat. Let's see what happens when the nutrient solution wets the garden soil. If the microorganisms reproduce, they will release carbon dioxide. It's 10 hours after the start of the experiment. Time to take the first reading.
Yeah, see, even the time intervals are different, right? Like, the last experiment was like 1 minute after whatever, but the first interval is 10 hours afterwards. So, yeah, we need to wait a lot longer to see the results of the life producing CO2. But, like, you will see the results.
Hardly any CO2 has collected.
Oh, what? Never mind. I guess you won't see the results. Screw me. Oh, but hardly any. So the next day there will be like twice as much. I guess 2 times 0 is also still 0, but I think they meant to put like, 0.0001. After a certain amount of time, you will get production. It's going to be exponential, as they described, I guess.
Ten more hours have passed. Now we have some CO2.
I wonder if they timed that bubble. Like, that was a very well-timed bubble for them to have. So I don't know. That was either very lucky of them or very, clever of them.
5 milliliters have collected.
That one bubble was 5 milliliters, I think. That's funny.
After the third 10-hour time segment, there are 18 milliliters of CO2. The reaction is speeding up.
Yeah, that's like more than doubly as fast as the previous 10 hours. Wow, that's almost 3 times as fast, actually.
These are the data after several more 10-hour intervals.
Oh, hang on. But that's the thing. So it increased very rapidly, it looks like, but then it also leveled out again because there's carrying capacity, there is limitations of resources in the environment, and there's limitations on all sorts of things. So I understand why it would level out eventually, but that's an interesting experiment nonetheless.
Each measurement shows a larger growth than in the preceding interval.
Yeah, it's kind of a hard data set to really make good, claims on because it's not going up perfectly exponentially, but it is going up and it's actually increasing over time. Like the second derivative is positive as well, right? Like it's getting bigger at an increasing rate as well. So I guess that is illustrative of life.
When the volume of CO2 is plotted against time, the curve shows a steeper and steeper slope.
Dude, this was one take that this guy got this line drawn in. Like, hats off to this guy. Like, that's an impressive line to draw in one go.
This is the characteristic curve we have called...
Like, look how good that looks like a computer made that.
...called exponential growth. This curve provides...
Like, he did that with his hand right in front of the camera. Like, he was nervous and he still got this curve. Like, I don't know. Is that a funny thing to be impressed by? Maybe.
Evidence of the presence of life. There are microorganisms in the garden soil. With enough nutrient solution, the microorganism colony is getting larger and larger. This is Death Valley, California, an area in the Mojave Desert with an extreme climate that is hostile to most life forms.
Oh man, Death Valley. What's funny about this is we're probably looking at Badwater Basin right here. If you guys watch my Atlas Pro videos, you'll probably, hopefully, be aware of Badwater Crater on Mars, and it received its name from this basin right here in Death Valley, known as Badwater Basin. So it's kind of full circle, but the people making this don't know that yet. We haven't named that crater after this place yet. So there's a connection to Mars here that doesn't actually exist yet in the time that we're watching.
There are few visible signs of life. A sample of desert soil is collected.
Yeah, it's going to take a lot longer to start seeing those first bubbles come up, but again, there is life. There is some sort of life in that soil, and once it gets going and it does start reproducing, you'll see the same pattern as we saw in the typical garden soil.
And a measured amount is added to the flask, just as in the garden soil experiment. The same nutrient is added to this soil, and the amount of reaction product, CO2.
Oh, hang on. So these are the results. So 0, 2, 3. Oh, yeah. So pretty much the same exact thing as well.
Is measured at equal time intervals.
Honestly, I'm kind of surprised how quickly it produced stuff as well. It kind of demonstrates that like there is an abundance of organisms in pretty much like any sample of soil on Earth, which I guess if you're looking for life on Mars tells you that you could probably just pick up any handful of dirt anywhere and test it all the same and have that be indicative of the planet as a whole, right? Like if you can go to someplace on Mars and not find any life there, I just feel like that demonstrates that there's no life anywhere. Except for like 30, 100 feet down beneath the surface. That is my one caveat, that there might still be life deep within Mars.
The gas measurement results are plotted. The exponential, ever-increasing curve shows that microorganisms are even present in desert soil. Life is again detected. What happens if we heat a sample of the garden soil in an oven to 160 degrees centigrade? At this temperature, most microorganisms are destroyed.
160 centigrade, so that's above the boiling point, right? Yeah, that should have killed anything in it. But again, there's contamination in a lab like this, so you will still get like single-celled organisms, but I wonder if that'll affect the experiment at all.
To this sample of heated garden soil, nutrient will be added. However, even after many days...
Oh yeah, there you go. So they completely sterilized it. But isn't that crazy? Because like, I feel like even having it open for like 1 or 2 seconds, you're going to get some microbes in there that can metabolize. And eventually you will get signs of life again. I don't know. That's just my expectation. Life finds a way, you know? So it's pretty impressive that they 100% sterilized that soil sample.
No gas is produced. There is no growth. The heat from the oven must have killed.
I love just watching the scientist draw a straight line over the straight line already. Like that's a good visual demonstration.
All the microorganisms in the garden soil. Comparing the plots in each experiment distinguishes chemistry associated with the...
Oh yeah, there we go. There's the leveling off of just the pure chemicals compared to the exponential continued growth of living soil. That is interesting.
Presence of living, reproducing organisms from the chemistry associated with other types of reactions. The life search experiment based on this principle of exponential growth is called the gas exchange experiment.
Interesting. I didn't know this actually had a full name, the gas exchange experiment. So my question is, have we conducted the gas exchange experiment using Martian soil? I know we've never brought Martian soil back to Earth, but I think what they're setting us up for is us putting a piece of equipment on one of the Viking probes in order to test for this. I have to imagine this is like the very first thing we'd want to do, right? Like this is the easiest way to detect life, is just adding water in nutrients, I guess, to soil. So I have to imagine this is the justification we used for putting something that recreates this experiment on the first Viking probe.
This is the apparatus with which the Viking gas exchange experiment was performed on Mars.
There we go, there we go. All right, so this is what conducted that whole experiment. Interesting. So yeah, it's pretty obvious that we did conduct this experiment now that I think about it. But I guess the results of this experiment were probably pretty disappointing if I haven't heard about it.
It seems a long way from a funnel, flask, and collecting cylinder, yet it is essentially the same, except for ruggedness of design to withstand the launch, the 440 million mile journey, and then the landing on Mars, and the ability to work on command from signals from Earth. The gas exchange instrumental package has a sterile test chamber.
Oh, this is so cool. We're getting to see like the schematics of the inside. Again, this is real engineering to the max right here.
Into which Martian atmosphere and a Martian soil sample can be introduced.
Hang on. So yeah, this let in Martian air with Martian soil, and it collected in this little thing. What is actually holding it inside of this thing though? Like, I don't know. This is interesting. It's definitely a good schematic, but I'm like, how is this little cup just floating around in this chamber? Like, what is the actual mechanism?
Nutrient is brought up under the soil sample, which is in a porous cup, to enable the growth of any microorganisms that may be present. Calibrating gases are added to the test chamber. Any gases escaping from the moistened soil sample mix with the atmosphere in the chamber. A stream of helium serves as a carrier gas. Samples of the atmosphere in the test chamber can be drawn off periodically for analysis by a gas chromatograph.
Gas chromatograph. Again, another like great old term for an old instrument that I can't imagine we use anymore. Maybe we still do use chromatographs in this context. It's just like, yeah, another word that I've never heard before.
This is an instrument containing a long coiled column of tiny special plastic beads. The gases enter the chromatograph. As they travel through the column, different gases adhere to the beads differently. A molecule of oxygen will stick to a bead a shorter time than a carbon dioxide molecule before it moves along.
So pretty much like these beads capture gases at different ratios. So if you have CO2, you can look for the part of the tube that is going to capture that and see if it has. This is very complex. I feel like I wouldn't have thought of this, obviously, but I feel like this is more complex than it needs to be for what it's testing. But maybe that's just me.
Hence, the oxygen will get ahead of the CO2 as the gases move through the column.
Okay, so that makes sense. So certain atoms move through gases faster than other atoms. So I guess it's based on like the size or the weight or the mass, I guess, of the compound determines how fast it moves through these beads. Again, very, very complex, but interesting.
So, measurement of the length of time that a gas takes to move through the gas chromatograph column determines what gas it is. At the end of the column, each gas encounters a filament heated by electricity. Each gas cools the filament, which decreases the electrical resistance.
Dude, this is so ingenious, but also like so counterintuitive. Like I feel like there must be an easier way to figure this all out, but I guess not. Like if NASA's doing this, then like this is the best method for sure. It's just like I've never heard of this being done before, so this is very interesting.
How much the resistance changes indicates the quantity of the gas.
Wow, so yeah, that's how we're detecting the composition of the gas that's resulted from the adding water and nutrients to the Martian soil sample, is we are seeing how that gas affects like the conductivity of a wire, and we're reading that. Oh man, that's very complex for sure.
The time it takes each gas to travel through the column
Oh, interesting. So yeah, you'll get a different reading. You'll be like, at this second, like this was the resistance. Then at this second, the resistance went down or whatever. So wow, yeah, I can totally understand how you would read these results. It's just this is such an interesting scientific device, a chromatograph. Like, what are the other uses of chromatographs? Are there any?
Identifies that gas. And the measurement of the resistance tells how much of that gas is present.
Wait, hang on. So the time tells you what gas, yes, and the resistance tells you the quantity. All right, so yeah, you look at when you see spikes of resistance, and it's like, all right, well, this experienced this resistance at 1 second, so that must be CO2. Then it experienced this resistance at this second, so that must have been O2. And then how much resistance is just how much of that gas was actually present. Wow, that's so fascinating. That's so complex. I never would have come up with this, but I think I do understand it.
On the 8th day after the first Viking lander settled onto the Martian terrain at Chrysi...
Oh, where is this? Chrysi Planitia? Oh, wow, Chrysi Planitia. All right, so it's right by the volcanoes, but it's inside the Valles Marineris, or it's at the entrance of the Valles Marineris. Interesting. That is a very smart place to look for life, because that is a place where water has been present very often in the planet's past.
Chrysi Planitia. The commands were relayed from...
Yeah, you know what? That's a pat on the back for knowing Chrysi Planitia, by the way. I know my Martian geography better than most, not to brag or anything, but yeah, a pat on the back for sure.
From Earth to begin the soil experiments.
Viking, this is Lander Lee. Go ahead, Lander Lee. We have the command file in...
Dude, can you imagine, like, the excitement that these scientists must be experiencing? Like, they must have worked on this experiment for years and years leading up to it, designing every aspect of this machine in order to test just the most simple of things, really. But then to wait and to launch it, and then to wait some more, and then for it to land, and then you have to wait 8 more days at least, and then you finally get to test whether there's life on Mars. Like, that's what we're testing right now, you know? Like, these people thought they might be getting the most, like, fundamentally amazing answer ever in, like, 5 seconds, you know? Like, that's what we have to remember, is, like, just how big the stakes of this experiment were. Like, this was going to tell us if there's life on Mars or not, and if there's alien life out there, you know? Like, this is... I can only imagine how excited these people must have been to press these buttons finally.
UN stack. Copy that. Verify the file load. Let's go active on. Roger.
This exact duplicate of the Viking lander at the Jet Propulsion Laboratory shows what happened on Mars. The Viking...
Oh, that's cool. That's cool that we get a reenactment using, like, a 1-for-1 model of the actual probe. That's cool. Well, hang on. What is this little, like, star icon? This looks like the ChatGPT logo, but, like, from 50 years ago. That's hilarious.
Collector head extended.
Whoa, I did not realize it was that long. I guess it's a grower, not a shower, huh? Whoa, that's got so much longer than I thought it would be. How'd they even fit that much tube in there?
Scooped up a sample of Martian soil and dropped the soil into the inlet. About 1 gram of Martian soil was dropped into the porous cup in the experimental chamber.
About 1 gram. See, it's so funny seeing these machines work, because to me, these machines look like so not perfect. Like, the way it's just like shaking the sand into that thing, but it's coming out on the other sides as well. And there's no like perfect timing to the shaking. Like, it's just like randomly shaking. I don't know if that's on purpose, but like, this does not look as official as I thought it would look. Like, it shakes to varying degrees and at varying time intervals. It's just like, who designed this thing to shake the sand? Like, I don't know.
It was dropped into the porous cup in the experimental chamber. At first, nutrient was added only to the bottom of the chamber.
So hang on, are we just going to watch this same exact animation over again?
Thus, at first, the soil was exposed only to water vapor from the nutrient.
Huh, interesting. Now, I guess that is an interesting question, but I don't think it would yield any different of results.
To the liquid itself. This precautionary step proved to be quite interesting. After 2.5 hours, the inlet to the gas chromatograph was opened. The gases above the soil sample were examined to see if anything had happened. The signals containing the results of the first experiments went from the lander on Mars, first to the orbiter, then across the millions of miles of space to huge antennas at Goldstone, California, Australia, and Spain. The signals were relayed to Viking science teams at the Jet Propulsion Lab in Pasadena, California.
Just like what's so crazy is like this could have been the message that told us there was life on Mars. You know, like this could have been one of the most revolutionary moments and discoveries in like scientific history. But it's not, because there was no discovery made. Well, that's not to say there was no discovery. I guess we discovered that there isn't life on Mars, but like that's not the same as discovering life on Mars.
First lots back. See. I know it came out. Calibration looks proper on that. Right, about as much as we.
Yeah, look at these guys. These are the guys responsible for looking over the data that will tell us whether or not there's life on Mars or not. Like, these are going to be the first people to know that answer, you know? That's so wild. And like, that's what they look like. This is how excited they are about it, where they're just combing over this sheet of data. Like, oh my God, I'm so excited for them in this moment. I'm also not excited because I know what they're going to find, but like, I'm excited for what they don't know they're not going to find.
Gases were found. The calibrating gases were recorded as expected, as was atmospheric carbon dioxide. But these 3 peaks were of special interest.
Interesting, these 3 peaks. I wonder what they are. I've never really heard of this experiment being done, so I truly don't know what the results are. My expectation is that there's not going to be any life-producing gases or any gases produced by life. There's only going to be, you know, some sort of chemical reaction taking place. But that's just my guess. Let's see.
Yeah, well, why don't we blow off this area?
I think that everything went right with the plotting.
No, the data points are right on it.
The times of the smaller peaks showed they were due to nitrogen and argon.
Nitrogen and argon, that's interesting. That feels like, I don't know, that feels like some sort of chemical reaction. Nitrogen and argon, but aren't both of those inert? I don't know. I think I know that they are inert, but I don't know how that would affect an experiment like this.
Evidently minor constituents of the Martian atmosphere.
Very similar to the results we got on our test.
Yeah, everything else looks.
Yeah, you can tell these guys are disappointed already. They're like, yep, there's no like giant peak for CO2. There's no huge exponential graph for CO2. But didn't they say this was only like 5 hours afterwards or something? Like, didn't you need to wait even on Earth like 10 hours before saying anything? Or at least like 20 hours or something? I don't know.
The large peak occurred at 181 seconds. Comparison to lab measurements showed it had to be oxygen.
Oh, wow, oxygen? Really? That's interesting. So, I don't know, there's so many like conclusions you could draw from that. Let's just learn what they have to say. Again, that could be some sort of like oxidation reaction taking place between these chemicals, but I don't know. Let's learn.
Was that there was even more oxygen produced than the amount of carbon dioxide produced.
Wow, that is interesting. More oxygen than even CO2. See, that would also tip me off, though. I'd be like, all right, so the metabolism is greater in one direction than the other. I don't know. That's irregular, I think.
Could oxygen be the product of some growth process on Mars? The time behavior should provide a clue.
A little more closely. This could prove to be a significant event. Yep.
The next day, the instrument on Mars was activated again.
Spacecraft 27. Let's load up command file. C-Pound 27. Copy. Foxtrot 221 for a transmit time of 16:50:48. And let's go idle 2. Roger.
The gas produced during the second day...
Oh man, look, everyone's here now. They're getting... I love how it's just a sheet of paper too. Like, that's what they have to read. It's just like a line on a graph, and they're just looking for big bumps that tell us that there's life or not.
Day was compared to the initial 24-hour oxygen production.
Yeah, this is the one that I'd be more excited about, honestly. Like, the one that only lasted like 2 hours, again, like that didn't even register on Earth soil. So this is definitely the one that's like more make or break than that first set of data.
Calibration. There you go. I don't know if it's quite that high. Take a look at
The total amount had increased, but at a slower rate.
Oh, dang, at a slower rate. So yeah, it probably is just some sort of chemical reaction in the soil, because if it was living, it would be increasing, right? It would be going up at an exponential rate. But since it's not doing that, we can assume that this is some abiotic reaction taking place.
Definitely higher. We expect it double.
On successive days, the oxygen increased, But each day the amount of new oxygen production was less than on the previous day.
On the oxygen.
Yeah, okay, yeah, that's pretty damning. It's not from a living thing for sure.
And this,
I'm glad like I understand this so well because of how they explained it too. Like they really did do a good job of leading me into the understanding so that I can actually assess their own data. You know, like the fact that I can read their graphs and know what I'm looking at is just a testament to how good of an educational program this whole thing is.
abundance. And this appears to be somewhat puzzling. I think we ought to talk about it, see if there's any ideas that we could toss around.
The form of the curve looks very much like a reaction rate curve or chemical equilibration.
I'm glad this guy is just coming up with the same thing I said. Like, yeah, that just looks like any regular chemical reaction to me.
By the 6th day of the experiment, hardly any new oxygen production was being detected.
Dang, that must have been so disappointing to learn. Like, these people probably were wondering about this, again, for years, for lifetimes even. And, like, just to get the actual data that just says no, like, that would be pretty soul-crushing. Pretty important information to have, I guess, but, like, the less interesting of the two options, for sure.
Let's load up command file.
On the 15th day after landing, commands were sent to the Mars lander to raise the nutrient level until the soil was wetted.
Oh, I forgot that we weren't even doing that part of it yet. So that was just interactions with water vapor. I can't imagine it'll be any different, but let's see, I guess.
The data that came in during the next few days was compiled and plotted.
Now, after that time, we noticed actually something of a drop-off in the oxygen abundance.
That decrease is really surprising, isn't it?
It seems rather strange that we would get this sort of behavior.
Interesting. So you were getting oxygen production from reactions that were taking place between the air and the soil, but when you actually bring the nutrient solution in contact with the soil, the production of oxygen decreased. I don't know how to explain that other than like you might have, I don't know how to explain that. The comment that this scientist just made was a very good one. That is a curious change. I wonder how they're going to explain it. I love how this is how the lead scientists on Life on Mars looked, by the way. Like the fifth member of the Beatles, pretty much. Like mustache, like freaking leisure suit, like popped collar, like two collars at once, like the hair. It's all so good. It's all so 70s. It's so funny knowing that this is the guy behind like the biggest study into Martian life at the time.
I think we have to...
Now the oxygen seemed to be decreasing. The results were again unexpected. Scientists in a number of laboratories hunted for reactions that would duplicate the results of the Martian experiments.
That is interesting that like we didn't immediately have some sort of context to apply that to. Like I would have thought that we would have known chemistry well enough to just have like an idea of what was causing that. But for people to be like, no, like this is an anomaly within Martian soil, within this experiment, and we have to try to figure out what's causing it. That's very interesting.
For example, in one such experiment, water was added to a mixture of dry soil and potassium superoxide, KO2. When we perform this experiment in our laboratory apparatus, we see that there is an immediate chemical reaction. A burst of gas is released, just as on Mars.
Is that just as on Mars though? Like I feel like it didn't release that many gases. Maybe some, but like I don't know. I don't think this was very similar to the experiment.
Then the rate of gas production slows down, also as in the gas exchange experiment on Mars. The slowing rate again characterizes a reaction in which the reactants are being used up. This is not the kinetic behavior of a growth process.
Yeah, that's what I was going to say. Like, it's going to slow down eventually because all the reactants are going to be used up. But I guess that's less impressive now that he just said it. But yeah, that totally makes sense. I don't know if that's actually that anomalous now that I think about it.
In fact, chemists know that superoxide plus water yields oxygen, the gas released in the experiment on Mars. This is readily verified by the ignition of a glowing splint. On Earth, the highly reactive superoxides are not found in nature. because any that might be formed would quickly react with water, which is abundant everywhere.
Interesting. Hang on. So if you poured water onto the Martian surface, would you produce a crap ton of oxygen? Is that like what they're saying? Is that there are specific compounds in the Martian soil that are very reactive to water, but the only reason they can exist on Mars is because there isn't water anymore? That is interesting. I never really thought about it like that. But that is certainly important for understanding the biochemistry of Mars.
Mars is so dry, superoxides could persist. But where would they come from? Scientists speculate that ultraviolet light from the sun might produce superoxides in the surface minerals of Mars.
Again, I think life is definitely deep beneath the surface of Mars. But yeah, at the surface, you're going to get all these weird sorts of chemical interactions with UV light and whatever else that, like, it's going to throw off your results no matter what. I'm telling you, NASA, drill 30 feet down and then swab for life, and you'll find different results. I don't know if you'll find the ones that we're looking for, but you'll find something different, that's for sure.
On Earth, not much ultraviolet light reaches the surface because it is absorbed by the ozone layer in the upper atmosphere.
Hang on, what map is this? Like, where on Earth are we looking at? Like, can anyone figure that out based on just this shot? Because I thought this was Labrador, but it doesn't look like anywhere on Earth, to be honest. I love how they're still depicting Mars with these, like, large straight lines cross-hatching its surface. You know, like, we should have known that there weren't canals on Mars. And this is not even what the Martian surface looks like. So you can clearly see that we didn't truly understand the Martian surface yet if we were still depicting it like this.
On Mars, the thin CO2 atmosphere lets almost all the ultraviolet radiation through, where it might energize constituents in the dry Martian soil to produce superoxides. If so, when the Martian soil was brought into contact with the water vapor in the nutrient solution, the superoxides in the soil would react to produce the rapid release of oxygen. As the superoxide is used up, the reaction would slow down. Later in the year, a second Viking lander descended successfully on the plain of Utopia, about 5,000 miles away from the first lander.
Hang on, Utopia, so that's going to be in the far north of the planet, right? That's going to be like the Utopia Planitia, that's going to be like the basin of the ocean. So this is what used to have water all those billions of years ago when Mars was really young. So I don't know if this is a better place or a worse place to search, because it's at the bottom of the ocean bed, but it's like you're not going to get any modern surface water in a place like this.
Identical gas exchange experiments were performed.
When we landed on Lander 2 and did a very...
Hang on, these are images of the arm that we saw, the extender growing arm. That's interesting. I'm glad that we took photos of where we took samples of. That like definitely helps understanding the whole thing more.
Similar series of experiments, putting the soil into the test cell and humidifying it. Again, we saw a large increase in oxygen, not quite the same size, but very comparable for all intents and purposes. And this is a large amount of oxygen in our test cell. You'll notice that it comes up and levels off pretty much, and then when a nutrient actually comes in contact with the soil, there's actually a decrease in the amount of oxygen. It doesn't look like biology to us.
Hang on, if you put a nutrient in the soil and the oxygen decreases, could it be using the oxygen? Could you actually be causing, metabolism to begin, and as a result, the oxygen would go down? I feel like if that's the case, you would witness CO2 go up. But that's only true if the life we're talking about is Earth life, where those chemical equations are the ones taking place. If there was another sort of gas that it would produce instead, who knows? Who knows if we'd really notice it or not? But I like to think that Martian life and Earth life would be very similar in that regard.
Biological response.
Here, the curve resulting from the Mars soil sample experiment is compared to the curve derived from the sodium carbonate hydrochloric acid experiment.
Yeah, it definitely looks more like that curve than the other curves.
And also to the exponential curve resulting from the garden soil experiment. The Mars soil sample curve is not like the exponential curve that indicates a growth process.
I just feel like there might be too much interruption as well, though, right? Because if Mars is going to have all these chemicals in its soil, like there might be a very trace amount of CO2 being produced from a life process, whereas the vast majority of it will be produced from a chemical process. So even though it's hard to notice any aspects of life in this graph, I don't think this is entirely damning either. It could just be incredibly trace amounts. Though even that, like eventually you would notice because it is exponential. So I don't know. Yeah, I guess this does pretty definitively say there's no real life in that soil.
Then, is it settled? Is there no life on Mars?
That's the question. Again, dig 30 feet deep and repeat that experiment and then get back to me. That's the only time I'll actually admit that I was wrong. I think life is on Mars. That's just, I'm going to say that, but I think it's only in very specific places.
Scientists cannot answer that question with certainty. Perhaps experiments with soil samples collected from other Martian terrains.
I love that. Just volcanoes? Question mark? Volcanoes? I don't know. Like, like that is, I guess, definitely reveals how like curious we were. Like, I don't know that we took 2 soil samples. What about volcanoes? Like, I don't know. Maybe there's something else there. Like, and what's so funny is that that's actually based on really good understanding. There are going to be different chemicals around a volcano. There are going to be different environmental conditions, climatic conditions around volcanoes, especially ones that persist years after the impact. I think it takes good intuition to predict something more around volcanoes, though whether or not there actually is life to be found around the volcanoes, again, unknown.
Other Martian terrains would give different results.
Yeah, riverbeds, that's another good one. I love how this is just question mark. Riverbeds, question mark. Like, that's so funny. But yeah, I think the riverbeds are another really good place to look for this sort of stuff. Because even though the riverbeds are dry, if you understand hydrology, you'll understand that subsurface water can still flow. Even if the surface is exposed to a low atmospheric pressure, there can still be water moving beneath the surface. So yeah, go to a riverbed, and that's where you should dig, 30 feet deep, and that's where you might find life still hanging around.
Perhaps a different nutrient is needed.
That's another good suggestion. If the life on Mars operates using completely different biochemistry, then this experiment is kind of bunk. Even though I bet water alone, like even without nutrients at all, water alone would still be good enough to replicate this experiment. So I don't know. That's good and bad. I don't know.
Perhaps growth takes several weeks instead of several days.
That's fair too. The Martian life might operate on a much slower time scale, not only because it's just weaker as a result of being on Mars, but also because of temperature. You have to understand that, right? The rate at which chemical reactions take place is determined by the environmental temperature. So if it was freezing cold in this little chamber, it does make sense that chemical reactions would happen at a much, much lower rate. Though I have to imagine NASA also thought about that and made this chamber like Earth temperature or something. Again, if you took Martian life and heated it up to Earth temperatures, that might kill it also. So it's tough. There definitely are reasons this experiment would fail besides the fact that there is not life in this soil. That's interesting for sure.
Thus, the evidence is negative, but not conclusive.
Negative but not conclusive. Yeah, I'd say that. Yeah, that's pretty much the most perfect statement you could say on this regard.
However, even if the gas exchange and the other Viking lander experiments gave no evidence that life might exist on Mars, they did show that it is possible for scientists to conduct sophisticated experiments at a distance of hundreds of millions of miles on the surface of another planet.
Yeah, this really is like the most amazing scientific advancement that had happened up to this point, right? Like, people walked on the moon in '69, but like, the moon and Mars are different, like people taking soil samples on the moon is one level of technology, but then having robots take our soil samples for us on a much more distant body is like, again, an exponential increase in the technological innovation at play here. So this really is impressive that we even conducted this experiment to begin with.
detect chemical reactions, identify the products, and measure their reaction kinetics. These techniques can be used at other sites on Mars.
Oh, that's interesting. Look, you're seeing women working at the NASA like Mars photography place as well. That's just, I feel like we need to appreciate that, right? Like these are the hidden figures, I guess. Maybe not quite, but you know, the hidden figure ladies for the Apollo missions. But like, this is another one of those interesting stories of like, man, how did these women qualify? Like they must have had, you know, great educations, great access to education. Like really, you really got to celebrate these women, man, because these women must have fought their way into this program, you know, like they must have earned their spot here so much harder than the rest of these guys. To even be allowed to be in this, I don't know, you gotta respect these ladies, man. And the men too, obviously. Like everyone in this lab is probably a super genius to some degree. But what you have to remember is that they really just did not want women in these programs. So the fact that they're here really just tells you that they fought hard for themselves and they advocated to be here.
On other planets.
Oh, I got bad news for you guys if you're expecting life on Jupiter. But I don't have bad news for you if you are expecting life on Jupiter's moons. Actually, I have some interesting news about that. I wonder if they know about that yet. Probably not. They definitely know about Jupiter's 4 Galilean moons, but I don't know if they quite understand like Io and everything quite yet.
Perhaps even in other solar systems.
Actually, yeah, Saturn actually makes a lot more sense. Doesn't Titan orbit Saturn, right? Titan, yeah. I think Titan is on Saturn.
The search for life will go on as we try to understand the place of mankind in the universe.
That's so interesting. Again, this is pretty much like the same conclusion that my video that I'm working on, that I'm watching this for, finds as well, that like we have to continue searching. That's the only option. There's no definitive way to end this curiosity without continuing to search. It's so funny to see pretty much the same exact thing I'm making already have been made with like way more interesting, you know, real life events taking place as well. So interesting, a very enjoyable program. I think that's the end though, right? Oh yeah, here we go. We got the credits. That's about it. All right, let's read the credits. The assistance of Frederick Brown, PhD, Viking biology instrument scientist. So that might have been the guy with the mustache we saw earlier. Maybe not though. And members of the Viking Project Jet Propulsion Laboratory, Pasadena. Okay, so yeah, pretty much everyone we expected to work on this. Dude, the music is hitting so hard. Like, I guess they're asking big questions in this program, so they felt like they needed music that was also, you know, asking big questions as well. This is definitely big question music. The director, Attila Demokos, this guy must have been Greek or something, and the Wexler Films, Los Angeles, I guess. I don't know what that means. Okay, and that's the end. All right, so that was a very interesting look at the actual science that takes place to discover whether or not there's life on Mars. I actually really liked this. Like, I don't know what I expected, but I'm glad we got to see, like, the scientific experiment, like, the data they received. Like, I feel like I actually understand the experiment that took place on Mars because of this. And obviously that's the point. I'm really glad we got to watch this. I feel like we actually saw science taking place. You know, we saw the act of receiving the data and poring over it and analyzing the results and making observations and asking new questions as a result as well. Like, this is actually science at play. Science in action, pretty much. Very impressive program right here. I definitely enjoyed this. This might be the favorite Mars one I've watched so far. I might have one or two more, but I also might finish my video before then. So we'll see if we continue in this series. I learned a few new concepts and some new laboratory procedures as well. So this is, yeah, very educational. I feel like I should have watched this in order to make my video. I guess I already made most of my video, but this definitely doesn't disagree with anything I say in my video. So I'm definitely glad I watched this. I feel like there is so much interesting stuff happening in this. I'm only more excited for all the people that were in this because they're going to get even more information very soon. So yeah, this must have just been such an exciting time to be a scientist, especially one of these sorts of scientists. You know, like this must have been, it's hard to describe how excited I am for these people and for them to discover more things. Because based on what I know about Mars now, they're never really going to get that satisfying answer, but they are going to discover things that point them in very promising directions, like the river channels and whatever. Like they are going to suspect that water has been here for a very long time, which is true. So it's just very enjoyable to watch. I will say I am glad we watched this. I wasn't sure. It was a bit long of a program, I know that, but I think we made it all the way to the end unscathed, and I actually think we gained a whole lot from it. So yeah, very enjoyable. I enjoyed this for sure. I hope you all did too, and if you did and you would like to help support this channel and what I do here, you can follow the link in the description that'll take you over to the Internet Archive. The Internet Archive is where I get all these old programs from, so if you want to support me, donate to them. Yeah, and with that, I think we're ready to cut to black.